Maybe can you explain a bit in a general way what is a quantum computer, what is this about, how does this work more or less in maybe just a general way, or what makes it different than a normal computer?
So the idea is that you can also use quantum theory for something practical, for not only for communication, but also for computation. And since regular computers operate on bits which only take states that are either 0 or 1s, and you send those 0s and 1s, process that information, and using multiple quantum gates, you can generate any algorithm you want. With quantum theory, you can do more, because your bits now, if they are quantum, they can not only take the values of 0 and 1, but also something in between. So to speak, they can be both 0 and 1 at the same time. And these quantum bits are called qubits, and a hypothetical device that could operate using qubits instead of bits would be called a quantum computer. And there are certain examples of algorithms that are known to run faster, much faster than any known algorithm that can be run on a regular classical computer. For example, the algorithm that is used to encode information in the internet, RSA, is using the idea that you cannot decompose large numbers into primes. Okay. That would take too much time on a regular computer. Now, there is a Shor algorithm on a quantum computer that would be able to do it much more efficiently. So if somebody had a quantum computer right now, he would be able to break into all the banks and steal all the money of the world, because all the privacy of communication between banks is based on classical cryptography that can be broken with a quantum computer. So that's why large companies invest a lot of money to be first to know that you can build a quantum computer, because in that case they can also look how to prevent that, and they will be kind of ready to prevent the catastrophe where somebody has the quantum computer and does all these things without anyone else knowing. So there is a lot of interest in this, and there's kind of arms race to build a quantum computer, and you can do a lot of interesting things if you had it.
Yeah, no, I think historically, whether we like it or not, there's always have been a certain like a political or economical interest in science, in the sense that sometimes the areas that can create that have more possibilities of creating some kind of technology that could be useful for government, for example, sometimes these areas can have more funding than others. So I think there's always has been like this sort of, I mean, because you mentioned this application of a sort of like a short algorithm, or basically breaking into banks and stuff like that. So I mean, there's always has been like this kind of, not secret, but like, yeah, this a political or socio-political interest in science. I think, I don't know, what's your opinion about this?
I mean, people have realized, since the Second World War, people have realized, the politicians I mean, that physics can be useful, and they notice it by seeing the explosion of the atomic bomb, which is a kind of explicit example how science can be applied in a way that changes the fate of the whole world. So that was the beginning of taking physics more seriously than before. And there were many other examples. I mean, all the technology is based on science, and every single big discovery already led to a complete revolution in everyday life. You can build new things with quantum, even with quantum theory already, like a laser or a computer that is built out of a little processor that has transistors inside. A transistor or a laser is a quantum device. So all the modern technology is already relying on quantum theory, and it seems that we can do much more if we make more efforts. So yeah, I think that there is a public understanding that science can be really useful and can change everything that we know. The way it can change the way we operate in reality. Not to mention that today's revolution of AI, that you can build these amazing algorithms that do things that were completely impossible before. It turns out that the only reason these algorithms work today and did not work 20 years ago is not because we have found a new way to build a device. The method, the algorithm is exactly the same. The machine learning algorithms are exactly the same. They were known 30 years ago. What we have now is the faster computers. We can run these algorithms in larger scales, and that's what is behind the success of these AI algorithms. And a quantum computer, if it was with us, if we could apply these machine learning algorithms on quantum computers, there is a big chance that the jump in the performance would be also amazing, would be kind of quantum leap. And this is another reason why you should really, I mean, first of all, you have to make an effort to try to build a device, but second of all, you have to be very careful what you do with it, because you can create a very, very powerful tool that would be maybe difficult to control. So I think there is a lot of challenge and a lot of responsibility also in the hands of physicists, because the tools that we provide can completely change the whole reality.
Okay, I see. I don't know what you think, but I think in the case of quantum computation, I think there has been a lot of progress. I think, and from what I understand, it seems like these algorithms that you mentioned, short algorithms, like in theory they work. Like we have the algorithms. In theory, they're proving to be more faster than the classical algorithms. But where I understand, the problem is that so far there is not like a fully functioning or that a fairly efficient device at actual quantum. I mean, there are some quantum computers, but they have errors. They're faulty. So I think right now a lot of the problems is to actually build a quantum computer that works well and can run these algorithms, right? Or
yeah, what is called so there are claims that people have quantum computers already. Yeah? I don't think this is the right thing to say. What people have is a device that does something that is non-classical, but the idea of quantum computer is something that is scalable, that you can build a twice as big computer if you just put together two chips. You cannot do it simply because the rate of errors that is introduced in the computation is too large. And in quantum theory, as you know, if you interact with something, you affect it, you destroy it, you kind of affect the content. And therefore, the problem is that the presence of environments affects the quantum computation, affects the state of qubits that are being used to compute something, and the rate of error is too large. You simply cannot efficiently error correct these errors. So if you have a classical computer, you send a big file from A to B, and you can send the file with 100% efficiency. You get exactly the same copy of the file that you have sent, which is amazing because you are sending huge amounts of data, and it's 100% perfect. There's never an error, not a single bit. How does it work? Well, obviously there are errors along the way. What happens is that the error correction codes they correct the errors, and they do it very, very efficiently. What we are missing is the same error correcting codes that are that efficient in quantum theory. And the thing is that you can efficiently error correct, provided that the rate of errors is not too large. And in classical theory, in classical computing, the error is not too large. There is certain amount of noise, but it's not destructive enough to prevent you from sending information. In quantum theory, it is so far destructive enough. So the struggle is to lower the error rates so that you can efficiently error correct.
Okay, I see. But I mean, just like as you said, I mean, there's obviously work to be made, but I don't think there has been progress, right? I think even like big companies, I don't know, like Google or IBM, they're actually like investing a lot of money, and it's just like they're advancing. I mean, we don't really know. I always try to be very careful in the sense that I think sometimes there can be a lot of hype, and I think sometimes people can be like it's hard sometimes to be objective, and I say that yes, it's very exciting, there has been a lot of progress, but I think there's also quite significant problems in terms of actually building these machines, right? Or I don't know, what's your opinion?
Yeah, I mean, I think if there was a quantum computer already built, we would already know. So I guess we don't have a quantum computer yet, and some of my friends are investing a lot of time and effort to build one, but I think we are still away. Okay. And again, it's just a practical limitation. In theory, if we could only lower the interaction with the environment, if we could somehow make the efficiency of all the operations higher so that there is less noise and more fidelity of these operations, we could have a computer today. Okay. So this is really a practical limitation.
Okay, I see. And for example, when it comes to algorithms, I don't know if I see it for you, but for me, it's actually, even though I have worked in quantum science or something, it's actually very amazing and sometimes mind-boggling how people can come up with some of these algorithms. Because I mean, I think one thing when I see Shor's algorithm, for example, like these things are not simple. I don't know, at least for me, it's
so
I don't know, just to think. Just to understand it.
Yeah.
Now, to actually think about someone come up with this, so these algorithms, I mean, I don't know, for me, I don't know how is it for you, but I think they're very hard. Like, there's like, it's not easy to come up with more efficient algorithms, quantum algorithms, than classical algorithms. So I don't know what's your opinion.
Peter Shor is a genius. I mean, the idea is really complex. It's not a simple idea. For example, quantum teleportation is a very simple concept. You can show how it works within 10 minutes. I'm teaching quantum theory to students, and just this week I was teaching that. And that took me like 15 minutes to explain what quantum teleportation is, how it works, what's the idea. With Shor's algorithm, it's really complicated because it's kind of has a little, I mean, it has a lot of steps. And they are, to me at least, they are not that trivial. So it's a different level of complexity. And the problem is that we don't have much more. We do know that quantum computers in principle can have an advantage, but we don't know exactly how we could use that advantage. For example, we know that there is a Shor's algorithm, although there is no proof that there is no similarly efficient classical algorithm present. We just don't have a proof of that. There is no known algorithm that is better, but there is no mathematical proof that there can be no better algorithm run on classical computers. So in a way, we are just scratching the surface. We don't, because all these advantageous algorithms on quantum computers seem to be quite complex. And perhaps what we could hope for is that AI algorithms will be better at finding improved algorithms on quantum computers. They are good. They found to be good in analyzing more complex systems than us. We humans are able to analyze simple systems, so that's why we simplify everything to something elementary and then understand it and try to generalize it. But AI algorithms are able to search through complex spaces, multidimensional spaces for some objects in these spaces that satisfy certain conditions. So for example, if you want to optimize something in a large space of possibilities, an AI algorithm could really be much more helpful. So who knows, maybe the future is with AI algorithms that will help us find better applications of quantum computers.